Dear learners, Assalamu alaikum. I wholeheartedly invite all of you to watch the video. Introduction. Our today's topic is various terminologies and probability, chapter 14, part 1. Learning outcomes. At the end of this class, the learners will be able to 1. Describe the various terminologies related to probability. 2. Describe the consequences of repetitions of an event. Main speech on the topic: pictorial representation of coins and dice. A coin has two faces. If we consider one face of it as head or simply ace, then the other face of it will be tail or simply tail. It's an unbiased dice. The top face of the above unbiased dice for a certain throw is representing the number 4. 1, 2, 3, 4. If this dice is thrown repeatedly, then the top faces of it will represent the numbers 1, 2, 3, 4, 5, and 6. It is very much essential and important to explain various terminologies on probability. Let us advance for this goal. Experiment. Experiment is an act that can be repeated under given conditions. Tossing a coin is an experiment. Trial. Any particular performance of an experiment is called a trial. As for example, any toss of a coin is a trial. Outcome. The result of any trial of an experiment is called an outcome. As for example, in throwing of a dice, any of the top faces 1, 2, 3, 4, 5, 6 is an outcome. Random experiment. If all possible results in an experiment are known, but not possible to know the result of a certain trial of it until it happens, then such an experiment is called a random experiment. As for example, the possible outcomes of tossing a coin are head and tail, but before the showing of top face of the coin in any toss, it is not possible to know which one of head or tail will come first. That is why tossing a coin is a random experiment. Sample space. The set of all possible outcomes of a random experiment is called a sample space and is denoted by S. Some examples of sample space. Example 1. Sample space of tossing a coin is S is equal to set of A's T. Example 2. The sample space of throwing an unbiased dice is S is equal to set of 1, 2, 3, 4, 5, 6. The elements of a sample space are called sample points. In the first example, A's, T are sample points, and in the second example, 1, 2, 3, 4, 5, 6 are sample points. Example 3. Sample space of tossing two unbiased coins at a time or of tossing a coin twice is S is equal to set of HT cross set of HT is equal to set of HH HT TH TT. We can write the sample space in another way. We draw two perpendicular line segments intersecting at a point and then write the sample points of this first sample space here and the sample points of the second sample space above the horizontal line segment. And then write H is HT T is TT. From this diagram, we can easily write the sample space. Set of H is HT T is TT. The sample space can also be written down by drawing the probability tree. I will certainly discuss about the probability tree in our next class. However, the number of sample points is always an exponential number whose base is the number of bases and exponent is the number of tossings. That's why without determining the sample space we can easily write then the number of sample points such as if the coin is tossed thrice then the number of sample points will be 2 cube is equal to 8. If the coin is tossed 4 times, then the number of sample points will be 2 to the power 4 is equal to 16. If a dice is thrown twice, then the number of sample points will be 6 square. If a dice is tossed thrice, then the number of sample points will be 6 cube, which is equal to 216. Example 4. The sample space of tossing 3 unbiased coins at a time or of tossing a coin thrice is S is equal to set of HT cross set of HT cross set of HT. We have already written the sample space of set of HT cross set of HT as set of H is HT T is TT cross set of HT is equal to set of H is HT HTH HTT THH THT TTH TTT. Every sample point of the first sample space should be associated with every sample point of the second sample space. Example 5. If both outcomes are numbers, then the sample point should be written down as an ordered pair. However, the sample space of throwing an unbiased dice twice is S is equal to set of 1, 2, 3, 4, 5, 6 cross set of 1, 2, 3, 4, 5, 6. In order to write the sample space, we should consider one sample point of the first sample space to associate every sample point of the second sample space, such as is equal to of 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. Example 6. The sample space of throwing an unbiased dice and tossing an unbiased coin successively is S is equal to set of 1, 2, 3, 4, 5, 6 cross set of HT. Following the same process, we should write the sample space as set of 1H, 1T, 2H, 2T, 3H, 3T, 4H, 4T, 5H, 5T, 6H, 6T. Event. Any subset of a sample space in a random experiment is called an event. As for example, set of 1, 3, 5 is an event of getting an odd number in the throw of a dice. Or an event is a set of specified outcomes that can result from a random experiment. As for example, set of 2, 4, 6 is an event of getting an even number in the throw of a dice. Some events, sure or certain event, an event of a random experiment which is sure to occur is called a sure or certain event. For instances, 1. The event of not seeing the sun at night is a sure or certain event. Example 2. If a dice is thrown once, then the event E of getting any of the numbers 1, 2, 3, 4, 5, 6, that is E is equal to set of 1, 2, 3, 4, 5, 6 is a sure event. Impossible event. An event of a random experiment which is sure not to occur is called an impossible event. For instances, number 1, the sun will rise tomorrow in the west or set in the east is an impossible event. Example 2, if a dice is thrown once, then the event E of getting a number divisible by both 3 and 5, that is E is equal to empty set, is an impossible event. Equally likely events. Events of a random experiment are said to be equally likely if taking into consideration all relevant evidences. There is no reason to expect one in preference to other. As for examples, 1. In tossing an unbiased coin, the event E1 of getting head and the event E2 of getting tail, that is E1 is equal to set of A's and E2 is equal to set of T, are equally likely events. Example 2. Event E3 of getting an odd number and the event E4 of getting an even number in the throw of an unbiased dice. That is E3 is equal to set of 1, 3, 5 and E4 is equal to set of 2, 4, 6 are equally likely events. Mutually exclusive or disjoint events. Events of a random experiment are said to be mutually exclusive if the happening of any one of them precludes the happening of all others. As for examples, number one, in tossing an unbiased coin, the event E1 of getting head and the event E2 of getting tail, that is E1 is equal to set of H and E2 is equal to set of T, are mutually exclusive events. Example 2, the event E3 of getting a number less than 3 and the event E4 of getting a number greater than 3 in the throw of an unbiased dice. That is E3 is equal to set of 1, 2 and E4 is equal to set of 4, 5, 6 are mutually exclusive events. But the event E5 of getting an even number and the event E6 of getting a number divisible by 3 in the throw of an unbiased dice, that is E5 is equal to set of 2, 4, 6 and E6 is equal to 3, 6 are not mutually exclusive events. In case of mutually exclusive events, there are no common sample points. But if the events are not mutually exclusive, then they have at least one common sample point. Favorable outcomes. The outcomes of interest of an event in a random experiment are called favorable outcomes. As for an example, if E be the event of getting a number divisible by 2 or 3 in the throw of an unbiased dice, then 2, 3, 4, 6 are the favorable outcomes of the event E. It is very much important to know about OR. In case of OR, we should consider all the numbers divisible by 2 first, and then the numbers divisible by 3 distinct from them. Exhaustive outcomes. Outcomes of a random experiment are said to be exhaustive when they include all possible cases, or when at least one of them must occur. For example, in throwing an unbiased coin, head and tail are exhaustive outcomes. But if some student selects positive integers at random and writes to form a set equivalent to the set n of natural numbers, then the outcomes are not exhaustive, as is impossible to include all possible cases here. If you have any query after watching the video, please let me know. The answer of your question will be given very quickly with utmost sincerity. With this, I conclude here. Thanks. Best of luck. In order to